We are now going to look at another example, but first, let's talk about the first shift theorem. Now, the first shift theorem provides we are now going to talk about the first shift theorem. The first shifting theorem provides a convenient way of calculating the Laplace transform of functions that are of the form f of t e to the at times gt. So you have a function multiplied by e to the minus at or e to the plus at. So any function, it could be a cosine function, sine function, t to the n, as long as it's multiplied with an exponential, either with the a to the with the minus at or plus at, etc., etc. It means that you are shifting in time. Either you shift the function to the left, or you delay the function, or you shift it to the right, whereby our a is a constant and gt is another function. And what happens is you take the Laplace transform of the entire function and you are shifting it with s plus a. You are shifting the function either by s plus a, or you're shifting it backwards. For example, if you have for example e to the minus at multiplied with another function gt, this one you are going to shift it s plus a. And if you have another function e to the at times another function gt, you're going to shift this s minus a times. And the best way to look at this is by taking an example. Let's say you have a function f of t is equal to e to the 2t times t to the third. So the Laplace transform of this function, let me take out this the lines. The Laplace transform of this function e to the 2t times t to the third is what we are going to find. That's the Laplace transform of the main function, meaning that the function f of s is equal to that. Now what we need to do is we need to identify what is our gt, and it's always easier. You take your gt to be this function. Don't take the e to the 2t or e to the 80, because your exponential function e to the something, it allows you to shift, meaning that you need to find the Laplace transform of this and just shift it. So here we can see that our gt is equal to t to the third, and what we need to do is we need to get the Laplace transform of that. So g of s is equal to the Laplace transform of gt, which is the Laplace transform of t to the third. And we've already looked at Laplace transform of power signals. So we say that the Laplace transform of t to the n was equal to n factorial over s to the n plus 1. And here we have t to the third. This implies that we have 3 factorial over s to the fourth, which is 6 over s to the fourth. Now we can apply the first shift theorem. So next, apply the first shift theorem, and to do that we let s is equal to s minus 2. So we are just going to substitute this part into this equation. Then we say, okay, f of s is equal to 6 over s minus 2 to the fourth. That's it. So you can see it's really easy to use the first shift theorem. Let's assume that you have now a function f of t is equal to e to the minus 5 cosine 3t. So again, what we want is this function f of s is equal to the Laplace of e to the minus 5 cosine 3t. So here we know our a is minus 5 and gt is, we are picking it as cosine 3t. And next we need to find the Laplace transform of gt. So we said g of s is equal to the Laplace transform of gt, and we know our gt is, we want the Laplace transform of cosine 3t, and we've done already the Laplace transform of a cosine function, which was s over s squared plus omega squared. So now here our omega is 3. So we're just going to write s over s squared plus 3 squared, which is s over s squared plus 9. Now we are going to apply our shifting property. Now remember, here we have a minus sign, so we are going to shift by a positive number. So we let s is equal to s plus 5, and we are going to substitute the s plus 5 wherever we have s. So we are going to have f of s is equal to s plus 5 over s plus 5 squared plus 9. You see, it's very simple. Let me do one more example, then we can leave this topic. F of t is equal to e to the 2t sine squared times t. Again, we're saying, okay, we want to take our Laplace transform of the time function, which is equal to the Laplace transform of e to the 2t times sine squared t. And with here we know a is equal to 2, and we can pick our gt is equal to sine squared t. And from trig identity we know, okay, so from trig identity we know that sine squared is equal to, sine squared t is equal to 1 minus cosine 2t over 2. So we can use this trig identity because we know the Laplace transform of a cosine. We worked it out already earlier. So we can say that, okay, let's find the Laplace transform of gt. So g of s is equal to the Laplace transform of 1 minus cosine 2t over 2, and we can pull this half outside so that we have this is equal to a half times the Laplace transform of 1 minus cosine 2t. And applying the linearity property of the Laplace transform, we can say that g of s is equal to a half Laplace transform of 1 minus the Laplace transform of cosine 2t. We know already what the Laplace transform of a constant is. We worked it out earlier. So the Laplace transform of a constant is 1 over s. minus the Laplace transform of a cosine, we've done that many times now, is s over s squared plus 4. Next, we apply the first shift theorem. Apply first shift theorem, and we do that by letting s is equal to s minus 2, because we have a positive 2 somewhere here. Okay, so do that. We have final result will be f of s is equal to a half 1 over s minus 2 minus s minus 2 over s minus 2 squared plus 4. That's it.